Any questions, anything, you guys?
About the figure of the figures of the 2025, which you said is a 2D picture from a 3D kind of.
Yeah,
So could you explain how we need to look at it, and is it a kind of superimpose
well,
compact?
it's an issue, right? So you look at this paper. Yes, we got this paper. So they're doing something unusual. Like usually to measure the persistence, you're gonna like do a scattering measurement and find the transition from 2 to 1. That would be one way to do it. Or you do a rheology measurement and you get the Kuhn length and you kind of figure out the persistence from that. Or you do a computer simulation, right? But they've kind of like got a new way to do it, you know. So it's kind of weird. Like so looks pretty good at face value, and the results seem to be right, you know. So so they're gonna see methods. So right here, so they make a dilute solution. They say in order to get the persistence length, you need a dilute solution for whatever reason, I guess aggregation or something. So they need a dilute solution. So they make a 1 microgram per ml. So we were doing mig per ml. This is like 1,000 times more dilute than that, I guess. We were doing mg per ml in the other one, and they said one for a rigid rod was a dilute. And this is 1,000th of that 1% one. It's pretty dilute. Like it's basically should be like in your mind, maybe it would be like one chain floating around, and there's maybe another one somewhere else, right? Like so super dilute. So they do that. Then they put us they're looking to see what the effect of salt. You do the ODF OSF model thing, which is somewhere here. Yeah, this guy, and it's on page, I wrote one page here, on page 1072 of that thing. So this is a kind of a reasonable explanation for this OSF. 72 there's a pit this thing. So this is the OSF model. So they have charges as part of electrolyte. There's charges along it. If it was straight, the charges would have an interaction like the distance a between the charges. But because you bend it, then the charges are closer together. So there's some balance of forces. There's a change in the energy of the chain because the charges come closer, and it's q squared divided by r is going to be the energy of the charge interaction. So basically, if you pull them together, r gets smaller, the interaction gets larger, right? So you get a change in energy by bending it, and then so the charges are resisting that bending. So bending is caused by thermal fluctuations, KT, and then it's resisted by the charges getting closer when it's bent. So it wants to spring back because the charges are there. That's the OSF model, as far as I understand it. I'm not an expert, by the way, but so anyway, they give some equations that you can't exactly read, and they finally get to maybe you could weasel through this and figure out what they're talking about, but basically end up with this equation, which scales the resistance length due to the OSF, which is going to be a linear sum. So you have the original persistence length and the added electrostatic persistence length, and this OSF is the added electrostatic one. So you have an original number, it's like 10 angstrom, 8 angstrom, and then you got to add on this thing's like 30 or something big. So it's going to be 40 total. That's how the OSF model works. You just add it together. That may or may not be true. It might be an inverse sum. I mean, they don't try that, but basically, simplest thing is just add them. So the gist of this is that it depends on the Debye length, this RD, which is 1 over the concentration, the square root of the concentration of the counterions. Okay, so, and it depends on the Beaucage length also, but basically RD squared, so you get the concentration of counterion, which is what they're doing. They're adding in counterions to the solution. So this 1 over concentration, RD squared is 1 over concentration square root, and then RD squared is going to be 1 over concentration. They expect to see what the persistence like goes with 1 over concentration. And if they get a plot of that, then they're going to get L0, which would be the number that they add to it. And the slope is going to give them the power 2 and the 1 over, or power 1 and 1 over concentration. So they get the power 1 here, and they get an intercept to get they get the L0 from that plot too. This is persistence. Oh, inverse screening length. It's supposed to be inverse squared here. This is supposed to be anyway. They get from these plots, they get the L0 from the intercept, and they get the dependence that agrees with OSF, which it should be this thing to the -2, not -1, right? That's what, why did this guy show up? It should be to the minus, oh, did I? This is a paper. This is one of these. Yeah, it should be RD is 1 over kappa. So it should be 1 over kappa squared, not 1 over kappa, what he shows here. I didn't notice that, but anyway, he says it agrees with the OSF, which should be this thing. And then you can get the 0 persistence from it, and then you get the electrostatic, and then I guess you get some other numbers from that. B is the charge spacing, which he knows. That's just that's because this is a right. So this thing is this alginate is a polysaccharide. So you got this isn't it. Monosaccharides is sugar, like glucose, or right. So it's usually a 6-membered ring. It's like this, and it can have boat chair conformation. This is chair that they're showing. Right. So this is actually glucose. So you can have so glucose can unzip and make a linear molecule just by it can rearrange. So it's got kind of isomers. It can go to a 5-member ring, hydroxyl sticking off, and be a 6 chain. It can be a 6-member ring. When it polymerizes to make cellulose or starch, and something like this alginate. So when it polymerizes, it's always in a 6-member ring, right? So it's going to have this, it's not conjugated, so it's not planar, right? So it's just a rigid molecule, one of which we can digest, which is starch, and the other of which we can't, which is cellulose. But some bacteria can digest cellulose. That's why cows and rabbits can eat cellulose and people can't. They have special stomachs with special bacteria in it. So anyway, otherwise we could eat wood, which would be really great, like because there's a lot of wood around. No one would starve, you know. In fact, people eat when they're starving to death, they eat wood and they find out it's not doing you any good, but it makes you feel better, I guess. You know? So anyway, except for the splinters, but anyway, so this whole saccharide thing is important, I guess, food science. Also these things. So this alginate, there's a video, I didn't link it, but there's a video of how they make alginate. So they start with seaweed, and they do this on an industrial scale in China. And all the pictures that you see in the videos are all Chinese people, but they say that in California they do it, and they say in South America and then England. But basically, the only video you'll see of large scale alginate production is Chinese people. And it's serious, like they have serious trawlers that go out into the ocean and they dig up like a ton of seaweed. There's also seaweed farms to make alginate. So it's an industry. And then it goes through a series of chemical engineering processes. It doesn't make it look like it would be good to eat. Like they go through, and it's all these salt things. Like they put it into acid first to dissolve it. So it's an anion. So they put an acid to dissolve the seaweed to get the alginate out. And they put in the cations to make it precipitate out. Like calcium makes it precipitate into this egg carton shaped thing. I mean, it's actually unbelievable that this many people are this interested in alginate, but basically this egg box model has 3,500 citations. It's like one of the most cited papers ever, practically. And it's basically that when calcium will make these little, the alginate will make little, like in an egg carton has like a cup. So these 6-member rings make a cup that holds the calcium in the middle. And then that links together and makes the alginate gel. So you can precipitate it out with calcium. So divalent cations have 2 arms to link with, so they can be like a cross-link site if they can find cations, if they can find anions on the polymer to hook to. Then monovalent just can stick on, like they can't do anything. All right, so the divalents are like going to make a gel, and monovalent are going to just mess with the bi-screen length things. Right, so he's looking at, and that's called a non-specific interaction when it doesn't make an egg carton. The specific in this context within this polysaccharide field means it's making an egg carton. Right, so anyway, so it's kind of like all these things, like you look at them, the little like rabbit holes that you go down, and it's like all of a sudden it's like, oh, that's pretty interesting. Like you could spend your life in these rabbit holes looking around and picking at things, you know. But so that's what these people are doing. You could say it's a waste of time, or you could say like, well, it's important to the food industry because this alginate they add to all kinds of food to make it thick, to thicken up a fluid. Like it's cheap because it's seaweed, I guess. And the process, it seems kind of extreme when you look at it. I guess you can do it on an industrial scale. It's just mixing things, and then it comes out to be this powder. You dry it. I mean, I guess it's cheap to make. It doesn't seem like it would be, but anyway, apparently it's really cheap. So you can just dump it into cosmetics, and it's non-toxic because it's like a bio thing and it's biodegradable. So it's got kind of pluses to it. And it doesn't have any reaction with people. So you can put it into biomedical things like the pharmaceutical industry uses a ton of this as an additive for pills because it doesn't do anything. Like there's no bioreaction to it. So it's nice stuff, I guess. Some uses, they found uses for it. I'm not sure how, it makes you wonder, like there's the ocean, there's the seaweed, and who thought of like the pills are going to be made of that? Like it's just because of over the series of time, and then this stuff was available and someone tried it. It's pretty weird how things happen like that, but there's probably a lot of other things you could use to make pills with, but this happened to be, anyway, so people are interested in it for whatever reason. If you small advances in it apparently has a pretty big impact factor, like 3,500 to find the cage thing it's impressive. Anyway, so that's alginate. Then so their process is they're gonna take this super dilute solution. Then they're gonna take a mica. So they're gonna cleave mica. So mica is a rock, and the nice thing about mica is that you can slice and you get a monatomic layer. So you can just crack it with a razor blade and you get like a monoatomic layer, which is perfectly, absolutely flat, which is of use if you want to do AFM. So you can take a probe across the surface and measure the potential between the surface and the probe and kind of look across and see what the structure is of the thing that's on this surface. So you want to have a super flat to start, because if it's rough already, it's going to be hard to see anything, say what it is, right? So they do that. The problem is that mica's got hydroxyls all over the surface because it's basically like silica, Si. So it's got silanol groups on the surface, which are anions. And the thing, this alginate, see, he shows it here. I've got the wiki. I hate it when this mouse does that. It just starts going nuts. I think he's got a picture of it in here somewhere. Maybe not. Maybe it's in the supplemental. Somewhere he's got a picture. So there's also a couple wiki things to show, but it's got this is a carboxylic acid here. So it's got a carboxyl double bond O, then OH. The H goes away and you have an anion, right? So this is different than cellulose. Cellulose just has hydroxyls on it. And this is actually the difference between cellulose and this stuff. Right? This has a carboxylic, which makes it a polyanion. And the chain goes along these ether bonds. Right, the oxygen single bond thing. So that's a key element that makes it an anion. Mica is also an anion. So I guess the idea is that you pour this onto the mica, it's not going to stick because the two anions repel each other. Right. So you need a cationic surface. So in order to get that, he goes to he treats the surface with this silane coupling agent kind of thing. So it's a triethoxy. So there's a picture of this too. I shouldn't open these here. Zeta potential that here. This guy. So he's going to stick this on the mica surface. This has 3 ethoxy groups on it, right? So those will hydrolyze with the OHs on the surface and make an SiO-Si bond. The ethanol flies off. That's a byproduct. It's a condensation reaction that condenses ethanol, right? So that'll make like a tripod. Silica is actually just like carbon. It's a tripod with a flagpole. But on the flagpole, the flag he's flying is a cation, an amine group, right? So that's like your standard cation thing. So they just flush the surface with this APTES, which, by the way, these things aren't good for you because they also will bond with the hydroxyls in your body, and then you have like amines where they shouldn't be in your body, and that can lead to all kinds of serious problems. So a lot of these functionalized silane coupling agents are kind of like nasty. In other words, they cause cancer and other things. So you have to kind of be careful. It looks like a nice chemical. It's got the little flagpole with a thing on it. It's nice, but actually these kind of amines have problems. That's why people worry about this tertiary amine surfactants and shampoo and stuff can kill you or something. I don't know, do something to you, right? So the cations, anions are nicer than cations. But as far as like performance in a shampoo, sometimes the cation is better. So whether you're willing to risk your life for shiny hair or whatever, that's an issue. Anyway, so they dump that on the surface. Just leads you to kind of a problem. So they're looking at the dependence of the structure of the polyelectrolyte by adding cations to the solution, small amounts. Right, and it has a dramatic effect on the structure, they claim, and it's also in theory. For instance, they end up seeing that the persistence length goes through this non-monotonic behavior, which means it doesn't go in one direction. It goes down and back up. So that's it. So basically, the down part is by screening, the up part is this counter-ion condensation phenomenon. Okay, so you get the bi-screening, and this follows nicely with the OSF theory, follows the device screening length, the persistence length change, goes with should be 1 over the concentration of counter-ion squared, or 1 over the concentration of counter-ion, 1 over the Debye length squared, right? So this part follows nicely with this thing, and you get the electrostatic persistence length from that, and the 0 persistence length. And this part follows nicely with this idea of this condensation thing, which he kind of describes on the paper. So the going up part, the down part is that you're screening out the charges. And the up part is this. So he says the larger mass ones have a bigger shift up because this guy's gonna think about it here. This always takes longer than what you expect. Zoom out. Yeah. All right, so it's basically like this. You have the chain, and then you have it's an anion, and then you first you're going to add in the cations, and they're going to screen, so you get this Debye screening length getting smaller around those charges. And finally, you reach the point where that U is 1, where you've added, there's a U potential between the charge, like E squared over KT. Those the counterions are moving around with KT. Finally, they balance with the E squared, so the chain saturates with the cations, as many as it could possibly get. Right, and then at that point, if you add more cations, the zeta potential reaches a constant. So at that point, you expect the zeta potential as you're adding the cations to go up and then reach a plateau, and that's where the counter-ion condensation begins. So any more cations you put on, gets stuck on the surface, but the potential at the surface, see, so this thing's negative, negative, I mean, if it's a sphere, it's negative, 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 then a plus. The first layer, then it goes out, exponentially decays down the charge versus distance. And then at some point it reaches zeta potential, which is the region where the shear flow of the particles, where the counterions aren't washed away by flow. So at that point you can measure, that's the effective charge of the particle in a flow field or in a diffusion field. It's moving around. Like the fluid, some of the counterions don't stick to it, it moves around. If I put a big field on this, then it's going to move. It's still got a negative charge. It's going to move towards the positive charge, and the motion of that, the drag coefficient of that's going to follow Stokes' law by the hydrodynamic radius, and the force that's pulling it is this electric field that you put on it, and then that's going to equal the velocity times friction factor. If you measure the velocity, it's going to be e squared times so the charge squared of the particle times somehow it's going to be related to the charge on the particle. That's the zeta potential that you measure. You put the field, you put the particles moving by a velocity, you measure that velocity, you know the friction factor from Stokes' law, and then it's going to be the potential of the particles in that field. Like that thing squared times the field will give you the effective force on the particle, and then you can get the zeta potential from that measurement. Right, so basically, you're measuring this charge on the outside of this condensed ions on it, and that's the zeta potential. And you look at it, it goes up and plateaus out. That's where you see this thing where it's saturated out. Then he says, well, the effect of that on the persistence length is that it's basically going to be like you have a chain, and you have these cations stuck to it as if they're like balloons. And then as the concentration of the balloons goes up, then the persistence length goes up. So you expect to see LP go up maybe to some point as you get more and more balloons stuck to it. These are the cations stuck to it. So the bigger the cation, the bigger the balloon effect. Yeah.
So the charges are meant to be equal and opposite, or the anions are supposed to be more than the cation.
The anions are more than the cations because the zeta potential is always negative. It never goes positive. But anyway, there's no reason why it would go positive, I guess, because it starts negative and then you counteract it with the cations. There's no reason you would get a net positive on it. Like it wouldn't just pile on more. It's only going to reach like neutral, right? But basically it doesn't reach neutral. It reaches, I think it's in the supplemental where he shows that. So this is a zeta potential. It does just like what he says, like it goes up and then plateaus out. So you reach a plateau, that's an ion condensation region. And that's where he's going to like 50 millimolar salt. And that's exactly where he sees the this going up, like 10 to 50, he says, is where he gets counterion condensation. So that's right where that plateaus out. That's where this goes up. And the bigger ones, the Mg is the larger of the cations. That's the one that has the largest effect. These are for different molecular weights of the alginate. So he's got 4 alginate samples. There's 2 molecular weights, 56, and then there's 2 molecular weights, and then there's two molecular weights, and there's 2 so there's 2 kinds of alginate. There's so there's 2 kind of isomers of this. There's this manuronate and gluturonate. Right. So basically it's just like, you see this is like going down and that one's going up. So they're both in the chair conformation, but it's like one chair is facing one way and the other one's facing the other way type thing. It's a 3D difference. It's like a stereochemical difference between the two. And when the alginate's made by the seaweed, it comes in blocks of M and G. So it'll be like 50 M's and 50 G's, but not MG. There's also blocks of MG. So So in the alginate business, they talk about the blockiness and they talk about they talk about just in terms of the blockiness. So he's got two types of this alginate with different blockiness to them. One's M dominated and one's G dominated. He describes it in here somewhere. Sample. Blah, 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 blah. I don't know if this is too much for you guys, but I read this stuff and I think like, oh, that's pretty interesting. But you might look at it and say, what the heck is going on? Either answer is correct, I think. But so the G content's 56 and 25. That's what he calls it 26 and 50, 25 and 56. And then they call it 8 out of G, 56, 25. Then of those two, well, he's got two, I guess he only has one molecular weight, sorry. So he's got two glutamate fractions, and he's got these two molecular weights. So 225,000 grams per mole, which is decent molecular weight. Then you look at that. So you'd expect, like, I guess I expected this was going to be a polydisperse molecular weight. You know, like in other words, you'd have a lot of short ones and some big ones, huge dispersion. And if you look at the pictures he gets, they look like they're like monodispersed. Like you don't see, you only see kind of, I only see like, all right, you can see whatever you want to see in these pictures, right? And he says there's a dramatic change. So I would really like to wager money with the guy if I cut these and made them into cards and he organized them for me, like from random, because they're exactly the same. There's no difference between any of the pictures, right? That's one of the drawbacks of this whole thing. There's several drawbacks to these pictures. Let me just, I have them listed, the ones I came up with right before class, you know. So let's see if I can read this. One problem is he's looking at the effect of cations on the structure of the anionic polyanion. Right, and then he sticks it to a cationic surface that's packed with cations. Like, isn't that a little weird? Like, wouldn't that affect the structure? That's one thing, right? Then, let's see, you can't, if you rearrange the micrographs, you can never could put them back in order. Like he says, this is an expanded rod-like structure for polycation, for, right, polyanion, sorry. And then these become like a random walk. And then these all of a sudden expand. It's not there in any of the micrographs. Like the reason why this one looks different, if you go back to he uses a software program called Fiber App that's from ETH in Switzerland. Which is a good place. It's like kind of like the MIT of Europe type thing. Then the reason this, if you go to their webpage or go to YouTube and look at the video of how you go through the process of using this, the contrast is all on your, like you do the contrast. The contrast is meaningless here. It's just powerful when you operated the program, what contrast you wanted, you pick it. So the fact that that's brighter than that is just, you could make that one brighter, that one brighter. It's just a, yeah, thresholding thing.
That's different magnification.
They're all the same. All right, that's another thing. It never actually says the magnification, but if you want to look, you can see it. So this is 200 something micron or some nanometer. So 0.2 micron. It's 200, 0.2 micron. So they're pretty large. I mean, 2000 angstrom. They're rigid rod polymers. I don't know, but they don't really look like rigid rod, you know, at all. I mean, they look like kind of self-avoiding walk, maybe. There's a lot of things about this, but his numbers come out great. So he might have made them up, but basically it's believable. Let's see. I wish I had written this more clearly. Yeah, I mean, they can do a couple things. Like you can say, well, is there any difference? And you can say, well, analytically, like I can kind of get the size of the chains here, and the size of the chains is supposed to change, like the total size, but the size of the chains doesn't change. That's one thing. And then the molecular weight distribution seems to be monodispersed, and I was expecting something pretty broad. But then I went back and he says he gets the molecular weight from another paper. These guys are in China, and then he gets it from another group in China, I think. Where is it? Yeah, this paper. This is where he gets the molecular weight. These guys did the similar kind of study. I'm not sure if these guys are in Shanghai, so it's a different school, I guess. Maybe the Chengdu is the same one. I don't remember. But anyway, they get the molecular weights, and the polydispersity is like 1, meaning that basically they're monodisperse. So you have, let me just say something about polydisperse, and I never said anything about that, but so if you have a distribution of things like, say, molecular weight, or it could be anything, right? So it's got a distribution. This is the probability. This is the molecular weight down here. So it's got some distribution curve. So you want to talk about like moments of it. So you take like, I'll sum all the molecular weights and divide by n. That's called the first moment. Say it's like m. And then you could do like, I'm going to sum the molecular weight squared and divide by n. That's the second moment. Or usually it's n minus 1. But, right. So you can do like, you can sum up anything. And then you could say like the square root of the second moment would give me a number. And if you did that, the first moment would be kind of in the middle. The second moment would be out here. The third is here. So as you get higher moments, you get a higher number. You get a higher number because the higher moments end up giving you because you're weighting each molecular weight by the molecular weight. And the molecular weight increases as you go across, so the average has to go higher because you're weighting it by a higher number every time. And then the higher moment you do, right? So polymer science decided not to use that normal scheme of talking about moments of things. So they decided they're going to go with this thing like they call that the number average, and then that's m. Then they have a thing called the weight average, which is m squared divided by m. Right. So that gives you units in molecular weight. That's kind of handy. So it's kind of the ratio of the moments. There's a thing called in the same sequence, since they already had that, and incidentally, this comes from light scattering. This comes from colligative measurements like osmotic pressure. Anytime you're counting the number of them, so molecular melting point depression, things like that, freezing point, whatever. So they said that this one, so different analytic techniques go with these different numbers. MC doesn't have a technique, but it's just an extension of this. So it's M3 over M2. Then there's the viscosity average molecular weight, which is some weird thing. It's like kind of like M to the A over M to the A minus 1 average, right? So an A, I forget what A is. It's like A is like 3 point something. 2, I don't know. Oh, A is 3.4, right? That's our molecular weight thing. So anyway, so there's all these different moments. So he's given MW in the paper. Then if you want to know about the distribution, well, how wide is the distribution? You take the MW divided by MN. That's called the polydispersity index. So he takes MW over MN, and he gets, I was expecting 2. That would be the normal number you'd expect. Polyethylene, when you buy it, is 16. And if you make an anionic polymerization that makes monodispersed, that's 1. Okay, so when you look in this paper, so his number is 1.3 or 1.2, which is pretty narrow. So I guess because it's a bio thing, wherever in here, it's narrow, and that's the micrographs show that narrowness, So anyway, if you go to the paper where he actually does it, that falls together okay. So the fact that they're the same molecular weight, that's okay. I guess 1.23 and 1.6 for these same 2 polymers. So. And then the other thing is that I said, like, he's making it at 1 microgram per ml, which is like, there's nothing there, right? Yet when you look at this, you'd expect to see 1 fiber for each of these micrographs, yet he has quite a few. And they're definitely way above the overlap concentration. Like you'd think, yeah. No.
Like the PGI you talked about.
Yeah.
It seems like the most probably. So the going to be higher, the broader the distribution will be, and the lower it is like the 1 point something. They have like,
I mean, it's supposed to wash it out because it's a ratio of two moments, you know. So you have the one over the n, and then you have the two over the one, and if you take the two over the one and the one over n, you have the two over the two over the one squared. I guess you end up with the second moment divided by the first moment squared is the PDI. That ends up unitless.
Yeah, so
But
if like the PBI, yeah, if it's larger, like if the value you get is like maybe above 2, 3, 4, does that mean the distribution is more broad? The uniform distribution is more
no, I mean, I think it's the reason that you're using these ratios to wash that out. So it's just the shape of the curve, I think. So the point of using the ratios is to get rid of that problem. So it's not, otherwise you'd use the standard deviation of the peak, which would be in units of molecular weight, and the higher molecular weight would have a higher standard deviation for the same polydispersity. So you can use this to calculate the standard deviation too. It's related to the second moment. Right, so so basically you can get the standard deviation from those moments if you want, you know, and it would increase with molecular weight, like what you're saying. The higher molecular weight would have a higher distribution for the same PDI, but the PDI is actually the shape normalized by the molecular weight, so it's independent of the molecular weight. I mean, the concept of it is to get it independent of molecular weight. So anyway, but if you want to get the effect you're talking about, you want the actual standard deviation, which would have units of molecular weight, and it would scale with the molecular weight that you have if it was the same shape. It's a good point. Anyway, so it doesn't look dilute. That's the problem with this too. And also, if it doesn't look dilute, it means he's got it, he's washing it. What he does is he washes kind of across that mica that's been treated with the amines. And then like he washes it a little bit and then he stops. He does it the same every time. But this is almost like a selection process. Like the ones that are more charged are definitely going to stick more. And the ones that are less charged are going away. And it could be that the molecular weight selection too is involved in it. That's why I was looking at molecular weight, because it looks like he's selected just high molecular weight. So there's a lot of selection processes in that thing that he's doing that he doesn't worry about. So anyway, but in the end, his stuff works pretty well. Like he gets a pretty good answer to this. So I guess you should be happy that this thing works. It would be interesting to kind of check it. The other thing is that, and I mentioned in the thing is that so you're looking at a chain that was in 3D, and you're talking about the 3D.
I want to ask, is there a reason why sodium chloride, potassium chloride, and magnesium chloride were used as the non-specific metal ions?
I think no, he didn't say why, but if you look at the process of making alginate, like there's an industry associated with this, and sodium is the ion they use the most for that. But then they use calcium to precipitate it out to make a gel. And then they also use these other salts sometimes to mess around with the separation process. So I think these are salts that are endemic to making alginate. I think they're tied into it. And also he's selected, maybe by accident, but ions that have different sizes, so different size balloons that would have a different effect on this ion condensation thing. And they have different affinity for the alginate, which he determines in the study, you know. So the affinity is just like so he uses the argument that they have different behavior, like the lambdas are different. So the lambda is a number that he comes up with. I mean, it might be in the field for all I know, but basically so he has the persistence length, LP and LP0 persistence length alginate chains with salts in 0 millimolar. So the LP0 is the polyelectrolyte normal huge persistence length. He has a salt and it's screened by the Debye. So he gets this is the shift in the reduction and the persistence length normalized by the persistence length. So since it reduces, this always has to be bigger than 1, bigger than 100, bigger than it has to be positive. Sorry. So lambda has to be positive because he's always getting a smaller chain. Even when he has the ion condensation, he still gets a smaller chain. Like, so it never, yeah. Well, I just want, so even when he goes here, he never gets back to the original. So this would be lambda 0. And then it's positive when it goes down because it's, yeah. Yeah, that's 0 salt concentration. So it's just the polyanion alone. So that's the longest persistence it'll have. And then the biscreen happens, the persistence gets smaller. So lambda P0 minus lambda P always has to be positive. So this always has to be a positive number. And then when you add the ones with more affinity have a bigger effect. And the ones that have less affinity have a small effect. And it turns out the ones that have less affinity are also the larger ones. So the Mg plus 2 is the largest of them. So he gets this sequence of these lambdas in terms of affinity from values for the chain collapse. Chain collapse is the Debye screening. He finds out the biggest. So magnesium has the biggest affinity. So the biggest lambda here, and then with the chain re-expansion, magnesium has the smallest re-expansion because this has to do with the balloon thing. So magnesium's the largest one. So the smallest lambda means it's the largest size. So it's actually the smallest lambda here means the largest re-expansion, because lambda is the difference between the largest thing it could get and the thing it actually is. So if it's small, it means you're getting to the largest it could get, but not quite. Kind of confusing. The lambda thing's a little bit confusing because a small lambda means big size. That's kind of the key thing here. So anyway, affinity, so they go in opposite directions. So it's kind of odd that we go in opposite directions with the ions, but he argues that this is an affinity effect here, and this is a size of the ion effect here. Which it makes sense. The whole thing is pretty neatly sewed together that you can't really rip it apart. But there are some kind of things that you wonder about, like how could you get such clean, nice data by doing this process that he did, and the whole thing seems screwy to start with. Like it seems like something where you saw it and you said, oh, we can probably get the persistence from that, but they didn't think much about like, can you really do that? And then they went ahead and wrote a paper on it, and then like afterwards you kind of look at it and say, well, can you really do it? Like, because there's a couple of problems with the selection process when you're making the sample. It's 2D instead of 3D. You're using the same ions to hold it to the surface, so you're looking at the effect on the chain scaling. So it's kind of like 15 different things could be explanation for why it didn't work, but it does work. So I guess you have to say it worked. Yeah.
Other question on figure 4. Figure 4.
Oh yeah. Right. Which is 4? That's 7. Right.
I know you explained it previously, but I didn't quite get it. As you add the cations, the persistent length decreases. Then it's like the first one you said is the OSF. The second one is the Debye. The last one is due to condensation. The persistent length increases.
Right.
I don't think you explained like for the first part why the persistent length decreases for the OSF.
That's just based on the Debye screening. So you add in the counterions, they screen out the charge. You add in enough counterions, the thing becomes as if it has no charge at all. Right. And the charged one is like a rod, it's fully extended. And the one, when you put in enough charges, it gets to be more worm-like, and then it just becomes like a random walk. When the charge is washed out completely, then if you keep adding charge, it still has some little bit of charge. And then you keep adding charge and this balloon effect comes on. Like you have these big bulky cations kind of stuck to it and it straightens it out.
So the OSF part and the Debye.
This is OSF, which is Debye, the same thing.
The same.
The OSF is explaining the Debye, quantifying the Debye screening in a polyanion, right? And then this is ion condensation, which is this kind of, the guy Manning kind of invented it, I guess. I don't know who he is, but in the OSF of these Norse people and some other people. F is a British guy, I think, Fixman, yeah, so, or maybe Fixman is a kind of famous guy, I forget, I don't know the details on him, but so. And he's like a theoretician, so. Anyway, yeah, there's two effects, it's not three. So it's just the device screening, which is explained by the OSF, and then this ion condensation thing, which is a separate thing going on. It's nice that he has, so those are the two main things about polyelectrolytes, so it's kind of nice you got both of them in this. And he's got kind of a quantitative way to talk about it. I mean, the problem is that the technique's nice because you can see exactly what's going on. The problem is you can't see anything. So it makes you think like, how could this possibly be working? I mean, I guess I'd like to be nice to be able to just have a different measure of what's going on here. So you could just say like if he had outlined some of these chains, I mean, some of them, like that one's fully extended pretty much. And some of these are kinkier. If he had outlined, like highlighted some of the chains, which is this program, if you look at the that fiber whatever program, you can do a lot, like as far as making graphics with it. Where it is, this thing, fiber app. Like you can see they did just that here, like the red lines are like highlighted fibers. So you can, the software itself does it, It's a nice software. See, he's just done outline of the fibers here. So I don't know why he didn't do that. These are dilute, right? Like maybe these are dilute or just that overlap concentration, which is different than what he has in this paper. Anyway, why don't I go through these questions in here and see what I got. Let's see. Below the overlap concentration. This is just the same thing, right? He says it's 100 times. I mean, with the concentration he put in, it should be 100 times more dilute. But if you look at the figures, they aren't anywhere near that. And he never explains why. That would be a useful thing to talk about. And then there's this other issue that if you take a 3D object, squish it into 2D, I mean, it looks more concentrated than it was when it was in 3D. Right. So it might be that might be partly what's going on. Like they're definitely stuck to the surface. Anyway, that could be part of the thing that makes it look more concentrated than the 100 times more dilute than overlap. So take your overlap coils, sketch them out, then pull out 9 out of 10 of the ones you drew. That's what it should look like. Right. And it doesn't look, there's no way it doesn't look anything like that. Even if you squish that flat, I'm not sure you would get it, So it's kind of like hard to see that. Then he gives this equation in the supplemental to calculate C star that's got some problems, Like it should be the mass divided by the volume, right? So he's got kind of a volume here, R3D by 2. I don't remember what R3D is. That's a volume, but this isn't really a mass, right? I guess L by L unit could be a number times L unit cubed. So this C star is a unitless number. 1 times 10 to the minus 4. So how does he get, I don't see exactly how he gets, then he says using that number to say it's 100 times more dilute, this microgram per milliliter, right? So anyway, so this equation, I think you should look at that equation and figure out if that's messed up or it doesn't have the right units, for one thing. And you wonder when it doesn't have the right units. Does it have the correct units for concentration? Doesn't make sense. So just look at that and see what you think. It might make sense, but you expect the overlap concentration to change with salt. All right, the other thing is that as the chains collapse and expand, their overlap concentration changes. It isn't fixed in the study. So he says he has a concentration, but as he collapses it, well, it should get lower. It should get higher with the collapse. So he should be in better shape as it collapses. When it expands again, it should be, so it goes like bad shape, better shape, and then not as good shape. But maybe he didn't kind of consider that the concentration, the structure changes with concentration, the structure changes, the overlap concentration changes. That's kind of a nuance, I guess. Maybe it doesn't make any difference. In fact, there's a persistence length from a single micrograph. So there's a statistical issue here. Like normally you do light scattering and you're literally counting billions of molecules, right? You get an average number. So, but here, I don't think he took more than one micrograph. He doesn't give any indication how many micrographs he took. It looks like he just used one. And there's only about maybe 40 chains in these micrographs. It's like averaging over 40 chains isn't sufficient to get an average number for persistence. I mean, I think it's not enough to do it. And he could take more micrographs and he could get to it. He's never going to get a billion, I mean, with micrographs. So this is always the problem with micrograph analysis of things. You're only looking at one thing usually. So, and the micrographs aren't necessarily randomly selected. So sort of complicated, all right, the process of making so a single micrograph and then complicated drying process. So it's not necessarily the same structure that was in solution that he's looking at. And then he uses a special equation for 2D persistence in this thing in the supplemental, I guess, somewhere. So he has a special equation for 2D persistence. That's good. But the fact that the thing is in 2D means it has a different persistence length. In other words, the persistence length in 2D in a confined geometry physically isn't the same number as the persistence length of like this is a special equation for 2D. It looks just like 3D, but basically he says it's different. But basically the LP isn't the same number in 2D as it is in 3D. No matter, even if it's the same, even if the equation's right for a 2D chain confined to a plane, the fact that it's confined to a plane increases the persistence. It has to because it doesn't have 3D to roam about with. So basically, there's a little bit of a problem with that. There's cast monolayer, Right, and the naked eye and the fiber app results don't seem to agree. Like your hunch about what's what, and the fact that you could never order the things properly if you were just given them randomly, kind of means that something isn't really fully explained there. And then the number of let's see. You can do a calculation of, what does it say here? Fiber app for a visible naked eye, any of the micrographs he shows. That is, micrographs could be reordered, What is the sufficient sample size? So 1 billion is a good number, I think. And calculate the number of Kuhn units in his chains. So he gives the persistence length is like so he lists the persistence length somewhere here, and then you can go into the micrograph and figure out how many of those are in a chain. So his persistence length is 28 nanometers. This is 200 nanometers. So that line is about like maybe maximum 10 units, right? And then you can figure out the chains are about, like, I guess I figured out that the chains were I think I said that I got the chains were about 50 units long, and each persistence unit, so you can figure out the molecular weight of the chains from that. And then you can also figure out the RG squared and everything if you figure out how many units are in it, how many step units are in it, Kuhn units. And then so Kuhn units twice so you had 28 nanometer for the persistence, so the Kuhn unit's going to be like 56. Right, so it's 56 nanometers per Kuhn unit. And how many 56, and the scale bar is 200, so a quarter of the scale bar, how many of those are in one of the chains? Then you can say, like, kind of what kind of chains are these? Like, anyway, that kind of analysis he doesn't do. It would probably be worth kind of glancing at that. That's what this is asking you to do. Then explain the OSF theory, explain it, like take a look at that paper, not this paper. Take a look at this thing, see what you can get out of it. I mean, basically what I said, it's like because it bends, there's a bigger energy, so the change in energy from straight to bend is related to the persistence length in the end, the added persistence length due to this electrostatic thing by balancing it against KT. So somehow maybe you can get that from this. If not, just do whatever you can do with that. What else? Explain why the polymer chain first collapses. This is the first part is the OSF, the Debye screening, and the second part is the ion condensation of the counterions, and then the zeta potential. I kind of explained that a little bit. There's some links to there's like wiki pages for zeta potential, laser Doppler velocimetry, electrophoresis. So those are all involved in measuring the zeta potential. And then so probably worth taking a look at that. And then this explanation has to do with the affinity. In the first part of the curve, it's the affinity leads to that. And the second part is that the volume of the counterions, the large to small volume, the balloon thing on the side of the chains. Right. That's why. And why is it always positive? Because you always have a less resistance length than the zero salt resistance length. So hopefully that's okay. It's kind of a lot, but hopefully it's all right. Seems like a lot, but yeah. It's always positive because you always have a lower persistence length than the one with no salt in it.
Okay.
So it always decreases, and there's a difference between the no salt and the salt. That's always positive. But it has to be positive.
The salt load.
Yeah, it always lowers it. Yeah. And that means that lambda always has to be positive.
Gotcha.
Yeah.